Hi guys, we're going to be going through the trial exam in this video. Now, initially I was going to do the trial exam in full myself and then go through the solutions with you guys, but then I figured, one, it might be useful to just see the thinking in real time, and two, obviously the actual reason, I didn't really want to spend 2.5 hours doing the exam and then another 2 hours or so making a video about it. So I'm just going to do it in real time here. The big disadvantage for you is that means you have to sit through me mumbling and fumbling my way through it. But hopefully there's some advantage in that, in you seeing how I'm thinking through these things. But obviously I'll try and put in chapter headings, so make sure you definitely shouldn't be sitting here for 3 hours watching me do this thing. Just skip to those questions that you need a bit of help with. Okay, so we might get a start. So what is this? This is the NEEP 2020 practice exam. And we're going to start with the multiple choice section. I'm just going to stop the video for a sec, so to give myself a little reminder each time I get to a new section, so that I can break the video up at those points. Okay, so let's quickly do that. Okay, all right, we're back. So just by the way, if you ever see me suddenly change lighting or change clothing, then you know that's where I've made a mistake and I've come back and fixed it up. Okay, all right, the multiple choice section. Question 1. We've got a pretty classic start to the exam where they just ask you some sort of straight up recall questions about gravity and electric fields. So this one is asking which of the following 2 correct statements about the properties of field types. So we've got statement 1, statement 2. Both of these need to be true for us to accept an answer here. The answer to this one is going to be C. The inverse square law applies to the magnitude of both field types. Only one field type can create repulsive or attractive forces, that's the electric field, whereas the other can only create attractive forces, that's the gravitational field. So the answer to that one is going to be C, and I'm not sure that one needs a whole lot of working out to go into it. If you go through the others, you'll find they're wrong for various reasons. Okay, so question 2, we've got a 6-volt RMS power supply, and it's connected across a 24 ohm resistor, as shown in the diagram below. Okay, and then this question is asking us which of the following shows the correct peak-to-peak voltage and peak current for the resistor. Okay, so I really don't think the VCAA is actually going to ask you about peak-to-peak voltage, but it's one of those things you stick on your cheat sheet and then you know it. So if we think about what our output voltage or input voltage even into this thing looks like, we've got 6 volts RMS, and what 6 volts RMS means is that sort of average level is 6 volts. Let me zoom in on this a little bit. There we go. So we get 6 volts there. So what are these peak levels here? Well, the peak is going to be something like 6√2 volts, and the trough, the very bottom there, is going to be -6√2 volts. All right, so if it's asking about peak-to-peak voltage, then it's asking about the distance from this peak to this peak, so peak to peak. If it just asks for peak voltage, it would just want that, but peak-to-peak is that whole distance there. So V P2P is going to be something like 12√2 volts. And when I look at my multiple choice answers here, I can only see one that's bigger than 12. 17 volts, that's going to be around about 12√2. So it's got to be D. So that means you can use that second bit as just checking, just a sort of a way of checking your answer. Okay, so let's check that gives us the right current. We got 6 volts and 24 ohms, so we can use Ohm's law. 6 volt RMS equals IR, so I RMS times R resistance of 24 ohms. And so I RMS equals 0.25 amps RMS. Now we don't see 0.25 here except here, but this is the RMS current. We want the peak current. So once again, we need to multiply this by √2. And when you do, you're going to get 0.35. Just by the way, it's hard to get this level of confidence, I know, but it is not a bad idea to just trying to get good at doing those quick sums in your head. Like, oh, it's about square root of 2, it's about 1.5. So 12 times 1.5 is about 18, 17 volts. And like being able, especially for the multiple choice section, being able to sort of just do the maths in your head without having to get out the calculator every time is going to help. You might very well find that you can tell the difference between your 4 different answers without ever having too many calculations. Okay. Question 3. We've got 4 charges of equal magnitude but different signs forming the vertices of a square as shown below. I'm just going to get my annotation out here. Sweet. So all of these are equal magnitude, but this one's positive, this one's positive, this one's negative, negative. Okay. Which one of the following vector arrows represents the direction of the net electric field? So net electric field means when you add all 4 electric fields together. All right, so what we need to do to find that is we look at point C and we say, what are the individual contributions of each of these 4 separately? And then only at the end will we add them up. Okay, so first off, let's look at this one here. Positive charges always create electric fields that go away from them. So at C, we're going to have an electric field that looks like that. This one here, same deal, but away from it. Negative charges create electric fields that come towards them. So this one's going to go towards that one, and we're going to have one pointing down this way. So we've basically got 2 fields, one that point up and right, 2 fields that point down and right. So the net field, the vertical components are going to cancel, but the horizontal components are going to add up. So B is going to be our answer there. Okay, question 4 is about the same question, but it's now asking about the magnitude. So it's saying the square has a side length of 1 centimeter. The value of each charge is 1 microcoulomb. Okay, so we've got 1 microcoulomb, 1 microcoulomb, -1 microcoulombs. Which one of the following represents the magnitude of the force of one charge of plus Q on the other charge of plus Q? So we're looking at the force of this one acting on this one and ignoring everything, nothing about C, ignoring all the negative charges, just saying what force would this one have on this one at a distance of 1 centimeter. Okay, so if we want to find electric force for point charges, not for plates and stuff, but for point charges, then we use Coulomb's law. So the electric force is equal to K Q1 Q2 over, not R2, R squared. So we've got a reverse square law. And then our Q's here are just, we'll put aside what K is for the moment. Our Q's here are each 1 microcoulomb, so that's 10 to the -6 coulombs. Our distance between them is 1 centimeter, so that's 10 to the -2 meters squared. And this one's squared as well because there's 2 different charges that both have a microcoulomb. So that's Q1 and Q2. And then, so we just need K. And in order to get K, we need to go to our formula sheet. If we go to our formula sheet, it's on the very last page, and here it is, Coulomb's constant. Always a good idea just to read what the value is as well as just looking for K, because you might find that the exam is using a different letter to what you normally use, or there's more than 1 K or whatever it might be. So just check that it is called the thing you think it's going to be called. Coulomb constant. Oh yeah, that makes sense. Coulomb's equation. So this is the K we're after here. So this is 8.9. I'm going to write it up here. Times 10 to the 9 Newton meters squared. Coulomb to the -2. Okay, that's good. The coulombs are going to cancel. The meters are going to cancel. And that's going to leave us with newtons. Good. Okay. So then we look at the options we've got, and we notice they're actually all the same except for their power of 10. So that means we don't really have to do this whole equation on the calculator. We can just look at the powers of 10. So this is going to be something like 10 to the 9 times 10 to the negative 12, because we're squaring that one, divided by 10 to the negative 4, because we're squaring that one. So that's 9, 10 to the minus 3, 10 to the minus 3 over 10 to the minus 1. That's 10 to the positive 1. Okay, so it's going to be A. Now, even if you didn't know about Coulomb's law, A would be the best guess here anyway. That would be the guess you should be making, because we're talking about microcoulombs acting on each other over like a centimeter. So it's a small distance, but it's not like microscopic. So we wouldn't expect it to be having a force of 10 to the 7 newtons on it. That would be crazy. And 10 to the 11 is really crazy. You know, the force on you of gravity is nowhere near 10 to the 7 newtons. So it would be wild if a microcoulomb thing were giving that much. So you could probably have just guessed A from the start, 90 newtons. Even that's quite a lot. Okay, question 5. Looks like it's about a generator. AC alternator connected to an oscilloscope is shown in the diagram below. And we get an AC output. And let's just check something. Are we using slip rings? Yes, we are. So AC makes sense because we're using slip rings. Which one of the following graphs best represents the variation in magnetic flux versus time? Okay, so if we think about what's the relationship between the thing we know, which is the voltage over time, and the flux over time, is that the voltage, or the EMF, is equal to negative the number of loops times the flux, the change in flux over the change in time. So the gradient of the flux, right? So the gradient of this graph has to match this graph. So already we can see that this graph here is saying there should be a 0 gradient at the first time marking, but this one here has a non-zero voltage, has a big positive voltage at that point. So that can't be right. So A is gone. B said there should, or once B says the same thing. B says there should be a 0 gradient at this first time marking, and we don't. We have a positive. We should have 0 volts. The gradient is 0, so the voltage should be 0. We don't. So A and B are out. Okay, C starts with a 0 gradient, and this graph here starts with a 0 voltage. Okay, that's a good sign. Then the gradient is negative, which means the voltage should be positive. Yes, it is. And then the gradient reaches a 0, sort of almost 2 marks in, and the voltage reaches a 0 almost 2 marks in. So C is starting to look pretty good, and C is in fact going to be the answer. D just I don't know what's going on with D. D's wrong for all the same reasons that A and B were wrong, and also is just clearly oscillating too fast. Okay. Question 6. Okay, 6 is about the same situation. Which one of the following best represents the voltage output measured by the oscilloscope if the connections between the coil and the oscilloscope were replaced with a split ring? Okay, so if we put a split ring commutator in here, then every half turn, we'd be flipping the voltage. We'd be making it, so we'd be forcing it to always be positive or always be negative, rather than going negative, positive, negative, positive. Well, it can't be A or C because those are just AC still. So it's going to be B or D. And then the question is, does a split ring commutator have any effect where it like smooths out the voltage? No, it just, all it does is just flip these negative parts of the graph up to positive. So D is going to be what the output of a split ring looks like. Okay. Okay, question 7. Student holds a rod that has a mass of 100 grams attached at this end and 200 grams attached at the bottom. They whirl the 100-gram mass in a horizontal circle while the 200-gram mass remains stationary. So as it whirls outwards, it's sort of pulling up the 200-gram mass. The radius of the circle is 30 centimeters. Okay. This is a pretty tough question, actually, to think through what's going on here. But the key is to say that, well, if this 100-gram mass came to a stop, what would happen? Well, it would suddenly get pulled in by the gravity that's acting on the 200 grams. So that 200 gram mass is going to pull downwards and doesn't want to be up as high as it is. It in fact wants to be 30 centimeters lower until this 100 gram comes in and hits the pipe. Right, so there must be some force which is pulling that 200 gram upwards to allow this guy to have 30 centimeters worth of leeway. And that means that the tension in the rope must be cancelling out gravity. So for question 7, our first step is going to be that the tension in that rope is equal to the mass on the 200 gram object times gravity. So that's 0.2 kilograms times 9.8 newtons per kilogram, which is 1.96 newtons, I think. Yes, is 1.96 newtons. Okay, then our second thing is to say, but wait a minute, that at the other end, what is that tension? Well, it's just the only force that's acting on that 100 grams towards the center of the circle. So that tension must be the centripetal acceleration. So it must be the centripetal force. All right. So it's the only force that's acting on that 100 grams. Now, it's true that there's gravity acting on the 100 grams as well, but it has no component in the centripetal direction. So we can ignore it. So that tension is, let's turn this into an approximately equals, is roughly speaking the centripetal force. Okay. So the centripetal force, though, is just mass times the centripetal acceleration, and that's what we're looking for in this question. We're looking for the acceleration. So, so we can just say 1.96 newtons equals the mass of the object. So this one is only 0.1 kilograms times some unknown acceleration. So the unknown acceleration is 19.6 meters per second squared, which is D. Okay, so D is going to be our answer there. Now, technically speaking, if we treated this guy, this 100 gram bob, as being down on a little bit of an angle from the pole, then what we would have is 1.96 newtons acting this way and 9.8 times 100 grams acting that way. So 0.98 newtons acting this way. And we would have to find some centripetal acceleration, which, well, we'd have to find what component of this cancels this out, find that angle in there, all that sort of stuff to find, okay, what is the actual net effect? What's the net force acting on this thing? What's the net acceleration, etc. I've made an assumption in here, which turned out to give me an answer that works. So I'm gonna say it's right. I've made an assumption that this angle here is really small, so that we can treat the horizontal component of this as being equivalent to the net. That's a bit of a flaw in this question, but hopefully you can believe that it is almost horizontal, such that the component of the tension in the horizontal direction is pretty much the centripetal acceleration. Now, let's move on from that. All right. Jane's going to stand on a weighing scale inside an elevator as shown below. When the elevator is stationary, the scale reads 55 kilograms. Okay, so she weighs 55 kilograms. At a different time, when the elevator is increasing its speed, the scale only weighs 53 kilograms. At this time, the force of Jane on the scale and the direction of the elevator's motion is this stuff and okay, so the scale is directly reading the force that Jane is acting on it with. So the force on the scale is just going to be 53 kilograms times gravity, not 55. Never mind what our actual mass is. The scale is reading that force. So it's going to be 53 kilograms times 9.8. And just looking at these possible answers here, I'm going to assume that must be 519.4 newtons. So the force acting on Jane or Jane on scale, is 519.4 newtons. It's a little bit weird to me that they didn't put in 55 times 9.8 as a distractor here, but we got lucky. Okay. Then at this time, the force of Jane on the scale, oh, we wanted the direction of the elevator's motion. Okay. So she weighs less now than she actually weighs. So when she was stationary, she weighed 55 kilograms. So that means the normal force that's acting on her now is less than the usual. Now that's what happens when you drop. So if the accelerator is increasing its speed, that means it's accelerating in whatever direction it's moving. So it must be accelerating downwards in order to reduce her mass. And the extreme version of this, remember, is if you're in free fall, then your normal force is going to be 0. So an extreme reduction. So we must just be going at, we're not quite in free fall, but we are accelerating downwards. So C is going to be the solution here. Okay, number 9. Two identical rockets of length L are traveling past each other at speed 0.8 c. Ugh, okay. Could have done with the diagram here. Neep. They're both the same length. They're both L. And they're both traveling past each other at a speed of 0.8 c. So I'm going to assume that's actually not super clear. I'm going to assume that means from the viewpoint of one, the other is going at 0.8 c. It's possible they mean that they're, from the viewpoint of someone in between, they're both coming in at 0.8 c. But I don't think there's sort of no third observer we can talk about here. Okay, so it must be this interpretation here. Okay. They are able to measure the length of each other's rockets. They travel past each other. Which one of the following statements about Maurice and Robin's measurements of each other's rocket is correct? Maurice measures Robin's rocket to be longer than L. Nah, no way. Always length contraction, never length dilation. And Robin shorter, Maurice shorter. Okay, that looks pretty good. Longer, shorter. Yeah, okay. So they both just measure. There's a lot of details in that question we didn't need. Whenever you're looking at something that's traveling with respect to you, it's length contracted. It is not length increased. Okay. That's why we call it length contraction. All right. A 1 kilogram ball is released from rest from a height of 10 meters above the ground. The ball strikes the ground at 13 meters per second. Which one of the following correctly identifies the energies as the ball falls from rest to the ground? Okay. All right, so you got 1 kilogram ball at a height of 10 meters. So we want to work out how much gravitational energy did it have initially. So that's 1 mgh, 1 kilogram times 9.8 newtons per kilogram times 10 meters, is it? Yep. So that's going to be 98 joules. So it's got 98 joules worth of gravitational energy at the start. And at the end, it has 0 joules. So that means gravity did 98 joules of work on this thing. Okay, so it's got to be A or B. Okay, but then not all of that work got put necessarily into the kinetic energy of the ball. So we need to work out how much kinetic energy it ended up with. So EK, well, EK initial is 0 because it started from rest. EK final is going to be, well, we're told that it's going at 13 meters per second. So if there was no friction or sound or anything like that, then we would know for a fact that this is 98 joules because all of this gravitational would get perfectly converted to kinetic. But we're being told that there's something else going on here, maybe. So we got to check this directly. So the ball strikes the speed at 13 meters per second. So we can use a half mv squared. So that's a half 1 kilogram times 169 meters squared, second to the minus 2. So a half of that is going to be 84.5 joules. Okay, so we know that gravity did 98 joules. We know that the energy the ball has when it hits the ground is 84.5 because it's only got kinetic at that point. So the rest must have been converted to heat and sound. Okay. Converted to heat and sound here is just code for friction. Okay. All right, let me just create another breakpoint in my video because we're up to question 10 now. And we're back. Okay, transverse wave on a slinky such that the energy travels 3 meters in 1.5 seconds. So we've got a wave speed there. So let's write that down. 3 meters in 1.5 seconds. That implies that the wave is traveling at 2 meters per second. And we want to know what the frequency of the wave is. And we're going to use this picture here. We can use this picture to work out a wavelength. Okay, so we have 1 full wave, 2 full waves, 3 full waves in 3 meters. So that means we have lambda equals 1 meter. So if lambda is 1 and v is 2, then F must be, V equals F lambda, F must be 2 hertz. So C. Okay. Students in a lab shine a beam of light of a single color through a single slit, and a single slit diffraction is not in the VCAA course anymore. Okay, they've missed this. Now, let's. If the width of the slit was increased, what would the effect on the pattern of bright and dark bands? So do not worry if you didn't get this question. It's been cut. But anyway, if the width of the slit increased, what would be the effect? There'd be no change in the pattern. Well, we would expect we'd expect a narrower pattern because diffraction is inversely related to the width of the gap. So we know that diffraction goes like lambda over the width of the gap. So if we have a wider gap, then we would expect a less diffraction, so the beam sort of gets narrowed. So we would expect them to become closer to each other. So C. So we'd expect a narrower pattern. Okay. Question 13. The de Broglie wavelength of an electron is the same as a 500 nanometer wavelength of a photon. Okay, so it's got a 500 nanometer wavelength, weird way of putting it. Which one of the following statements about the electron and photon is correct? Okay, the electron and photon have the same momentum and total energies. That is not true. They have the same momentum because we know that de Broglie wavelength equals h over p, and we also know that the wavelength of a photon equals h over p. So if they have the same wavelength, they definitely have the same momentum, but it doesn't follow that they would have the same energy. Energy is worked out by, well, all sorts of things, gravitational energy, chemical energy, all sorts going on there, but also even just kinetic energy. For the electron, it's going to be kinetic energy equals a half mv squared, or this new version where we write p squared over 2m. For the photon, its energy is hf. Those two formulas are not in any way the same. Okay, so the energy of an electron and the energy of a photon are very different, even if their momentum are the same. And that comes from the fact that the electron has mass energy, right? It has energy even when it's just sitting still. Okay, so we want same momentum but different total energies. So that's going to be B. Yeah. Okay, question 14. A photon of blue light has a frequency of 6 times 10 to the 14 hertz. The best estimate of the photon's momentum is blah, blah, blah. So this is just a straightforward application of the de Broglie wavelength equation. So, or even the just photon momentum equation. So lambda equals h over p, or p equals h over lambda. But we don't know lambda, we know the frequency. So we got to plug in for frequency here. So that's going to be hf over v, where v is the wave speed, and that's going to be c in this case. So it's going to be hf over c, which is actually the energy of the photon over c, and that's a formula that you could remember if you wanted to. And we can just plug these numbers in now. So let's do that. Frequency is going to be 6 times 10 to the 14. C is going to be 3 times 10 to the 8. H is going to be, now you might wonder which H you should use, the Joule one. Whenever we're talking about momentum, we're going to use the Joule version. The reason is that we need the units to come out in kilograms and meters and seconds and stuff, and joules are in that system of units. Electron volts are in a different system. Okay, so so we're just going to plug those numbers in. Let's do it. Oh, actually, I'm not even going to plug the numbers in. If I look at this, look how different all the powers of 10 are here. So I actually don't even need to worry about these things here. If I just plug in my powers of 10, I'm going to be okay. All right, so H is, so P is going to be something like 10 to the negative 34 times something like 10 to the 14 divided by something like 10 to the 8. Okay, so that is 10 to the negative 20 over 10 to the 8. So it's something like 10 to the negative 28. And I look down this list here, and the only one that's anywhere close is C, 10 to the negative 27. So C is my answer. Once again, that instinct to get out your calculator straight away can be fought. Look at the possible options and say, are they really close enough that it even matters, right? Or can I actually just do this sort of intuitively? Okay, question 15. Marie is standing in a large hall and is positioned 5 meters from speaker A, 3 meters from speaker B. As soon as I see that, I'm thinking, oh, the difference is 2 meters. Path difference, 2 meters there. Both speakers are identical. When speaker A is switched on, Marie hears a single note played at constant volume. While the note from speaker A is still playing, speaker B is switched on and plays the same note with the same volume output. Okay. The volume of the note now seems lower to Marie compared to when speaker A played the note. The possible wavelengths of the sound played by the speakers are 1, 3, 5, whatever. Okay, so we are looking for what could the wavelength of sound be here such that it produces a node where Marie is, because she hears it quieter, so she's getting destructive interference. So we want to put a node where Marie is. So our condition for a node is that n times lambda equals the path difference, and in this case the path difference is 2 meters. She's 5 meters from one, 3 meters from the other. Okay, that n looks like a squiggly line. Apologies. Okay, so lambda better be equal to 2 meters divided by, oh, sorry, n's got to be, so we want a node. So n needs to be a half integer. So let's go n plus a half. So I know that's the formula you guys use. I tend to think of n, I just think of it as a half, 1.5, 2.5, 3.5, but you can also just think of it as an integer with a plus half on it. So the possible wavelengths here are going to be, lambda could be, well, 2 meters divided by a half, so 4 meters. 2 meters divided by 1.5, so I don't know what that is. 4/3, 1.33. 2 meters divided by 2.5, so that's 0.8 meters. 2 meters divided by 3.5, probably not going to require that. But 2 divided by 3.5 is 0.57 meters, and so on and so forth. So we're going to go to this list here, and we see that option D gives us 0.8 meters, 1.3 meters, and 4 meters. So D is going to be right. So yeah, so the insight there was we know the path difference, and we know that nodes happen at half integer multiples of wavelengths being equal to the path difference. So we plug in, half a wavelength, 1.5 wavelengths, 2.5 wavelengths, etc., as the path difference of 2 meters. Okay, almost there. Might have to take a break after multiple choice. I know you're not allowed to, but you don't have to talk while you're doing it. All right. Which one of the following best describes the condition that results in resonance? Interference of two traveling waves that produce a resulting wave. That's just superposition. Interference of two waves at a point resulting in the production of a different wave. Also just superposition. Interference of a wave and its reflection created with a frequency that is natural to the medium. Yeah, I'm not sure how explanatory it is, but it's better than the others so far. Interference of many waves resulting in high amplitudes of energy. Okay, so that one there kind of suggests that it's just because we got lots of waves rather than anything to do with the having the correct frequency. So C looks like the best answer here. Okay, so resonance is all about when an object has a natural frequency that it wants to vibrate at, and you hit it with that frequency. So that's the only one that kind of really gets at that. It's not the best definition of resonance I've ever seen, but it's getting towards it. Okay, question 17 looks like it's about double slits. An electron beam gun projects electrons one at a time towards a double slit. Electrons are projected on the same speed. After some time, interference pattern is observed on the screen, blah, blah, blah. On the other side of the double slit, electrons are observed to strike the screen one at a time. Bam, 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 bam. The pattern of electron Yeah, this might be one where I need to come back after seeing the solutions. I would say at least 3 of them are correct. No, all of them are correct. Hold on. Okay, the pattern of electron strikes on the screen indicates that the electrons display wave behavior. Yeah, there's interference going on. There's nodes. Electrons display particle behavior. They're observed to be striking one screen at a time. So yes. Behavior of electrons depends on the size and separation of the slits. Yes. If the slits were really wide, we wouldn't have any diffraction. So they'd just pass straight through. If the slits were closer together, we'd have a different pattern. It does depend. And electrons display both wave and particle behavior. Well, yeah, because A and B are true. Okay, I think D is probably the most correct. I think what they're doing here is they're saying A and B are less correct because D says both of them are. And then C, maybe by behavior they mean not the specifics of the situation, but just the whole fact that they are interfering and so forth. That doesn't depend on the size and separation. Like the same thing will happen, but the details would be different. But the behavior, I suppose they could say, would be the same. Terrible question. I'm sorry. Let's move on. Okay, so we're going to do question 17 now. Sorry, 18 now. The first time I did this set of questions, 18 to 20, I got really angry at the questions. So I'm going to try and repeat this section, maybe without the anger. So a group of physics students are interested in determining the fall time of a tennis ball from a height of 5 meters. The students release the ball from rest and measure the time it takes for the ball to strike the ground. They undertake 5 trials, all conducted in the same way. The students record these results, and they have an uncertainty on their measurements of 0.1 seconds. They also perform a calculation and believe that the true result is 1 second. The students choose to discard the 1.5 second measurement. Okay. So this is a bad experiment, and I got really angry at it last time, but I'll try and ignore that as much as possible. The bit that I'm particularly concerned about is this bit here. They believe the true result to be 1.0 seconds. I don't know what that means. What is a true result? That's meaningless, and no person who has any business in physics should be talking about that. The true result is what happened. So it's very annoying to me, but I'm going to try and keep that in check. which one of the following represents the error in the 1.5 second measurement? So this is where this really plays a role. The actual error, so the error is the difference between what really happened and what was measured to happen. So the error in the 1.5 second measurement is what they want you to say is 1.5 seconds minus 1 second, because 1 second is the real value and 1.5 seconds was the measured value here. I would just say that that's wrong, and that's a misunderstanding of what errors are. But that's what they want you to do. So they want you to take the actual the value measured and minus off the real value, as if the real value is a thing that you can actually know. I don't know. It's what they want you to do. It's dumb. Hopefully the VCAA doesn't have anyone writing questions who's this dumb. But there you go. Not this dumb, I shouldn't say dumb, just who doesn't understand errors in that way. So yeah, so they want to be there, even if I don't agree. Okay, once the 1.5 second measurement has been discarded, the set of 4 remaining measurements is best described as precise and accurate, accurate and certain, precise and true, accurate and true. And this one, the reason that it's not B, C, or D is that certain and true don't have specific meanings at all in science. They're just English words. Precise and accurate do have meanings, and so we just better check that these two things do have that. Accurate, we'll come to in a second, because that's a harder one. But precise, yeah, I mean, we're measuring them to the nearest 0.1 seconds. We're measuring something that's taking 1 second to happen, so it's like a measurement of 10%. It's not the most precise thing in the world, but it's relatively precise. And more importantly, for precision, is that they're all clustered within 1.1 seconds of each other. So it's as if so whatever we're doing here, we're finding that the same answer comes up again and again and again. So there's not much random error involved. Okay. Accurate, well, so that's why they had to put in this fudge thing here, is because they want to say these results are accurate, but you have no way of knowing that without knowing whether there's systemic errors involved here. So accurate means, are these actually measuring the thing they say they're, are they actually measuring things correctly? So because they've done this fake calculation, we're going to say yes, they are, because the average of these ones is roughly 1 second. So once again, not my favorite question. Anyway, and then this one's even worse. The last 4 questions in multiple choice are all terrible. If the students had used different balls in each trial, for example, a marble, golf ball, tennis ball, squash ball, and ball bearing. Now, when I first read this question, I thought they meant they repeated the experiment with 5 different balls. But actually they mean they used a marble for one of the drops, and then a golf ball for a different drop, and then a tennis ball for a different one, squash ball. So these 5 results here come from 5 different balls in this imagining. Then the data set obtained would have had a different measurement of uncertainty for each trial. Well, I think the measurement of their uncertainty here is coming from the actual timing itself. So that probably wouldn't have anything to do with the balls dropping. Okay. The difference is that using different balls, dropping balls, producers are going to be systemic differences, biases in our results. Have rendered the experimental method unreliable. So remember, reliability, that's all about whether somebody else could come along and get the same results as you if they were to repeat the method. And like, as dumb as this method is, somebody else could do it, and they would expect potentially to get the same sorts of results, assuming that all the other, like lots of other things were controlled for. Have had more than one independent variable and semi-non-comparable. Yeah, so that's what's happening here. I don't even know if there is an independent variable in this. I don't know that anything is actually changing from one trial to the next. So maybe more than one is a stretch, but it's certainly the case that the trials are non-comparable, because we're in a very big way, we're changing one of the conditions of the experiment unnecessarily between trials. So there's an extra independent variable in there that we're not talking about. And then D, the data set would still have been reliable to achieve the aim of the experiment. Well, the aim of the experiment is to determine the falling time of a tennis ball Well, I mean, clearly using balls other than tennis balls is not a reliable way to achieve that. So so I think like I wouldn't quibble with anyone who wanted to say B here, because it does make it a little bit unreliable in the sense that, well, we only have one measurement of the actual thing we're trying to measure. But probably C is the more correct one here. But I'd be happy to hear arguments for B and C. Yeah. Yeah. Anyway, that's the multiple choice section done. I'll put the short answer into a different set of videos. Okay, so that's the end of this video.